This morning we're going to discuss our microwave engineering program. I would like to begin by talking about the characteristics of microwaves and then describe our activities in this field. These remarks will be directed mainly towards microwave cooking because it is now the most promising field for the use of this type of energy. Microwave heating differs in the form of energy and the method of getting heat into the food. The same amount of energy, however, is needed to raise a pint of water 100 degrees Fahrenheit, whether the heating is done in a hot oven or a microwave oven. Microwave energy is transmitted from the magnetron which generates it to the material to be heated in the form of electromagnetic fields. We will not try to explain what electromagnetic fields are because the details are quite complex and involve higher mathematics. However, there are many uses of electromagnetic fields with which we are all familiar. Both radio and TV broadcast their energy in the form of electromagnetic fields. The main difference between the electromagnetic fields used for radio, TV, and heating is the frequency of the field. Electromagnetic fields may have frequencies from just over DC, or 0 cycles per second, to over a billion cycles per second. In other words, we go from our 60 cycle energy and below up past the visible light range in the electromagnetic spectrum. As examples, WMAN broadcasts at a frequency of 1.4 megacycles. KYW-TV, Channel 3 in Cleveland, broadcasts at 63 megacycles. WJW, Channel 8 in Cleveland, broadcasts at a still higher frequency of 183 megacycles. Now, the ultra-high frequency region extends from 300 to 3,000 megacycles. In the bottom portion of that band is the UHF TV, which occupies the 400 to 890 megacycle band. Just above that is one band that may be used for dielectric heating with a center frequency of 915 megacycles. We have a magnetron which will operate at that frequency that puts out about 2.5 kilowatts of power. The microwave oven operates in the upper portion of the UHF band at 2450 megacycles. The word microwave means short wavelength. The wavelength depends on the frequency. The higher the frequency, the shorter the wavelength. Microwave frequencies are those from 300 to 30,000 megacycles. Wavelengths of microwaves vary from just over 3 feet to a fraction of an inch. Compare this to the wavelength of 60 cycle energy, which is 3,120 miles. The wavelength of 2450 megacycles is 5 inches. Now, why do we use microwave frequencies? Electromagnetic fields will travel down hollow pipes if the pipe dimensions are large enough with respect to the wavelength. 2450 megacycles, as we said, has a wavelength of 5 inches. Now, the smallest rectangular pipe for transmitting this frequency's energy is about 1.5 by 2.5 inches. Formulas tell us that to transmit the energy of WMAN down a rectangular pipe, the pipe would have to have the cross-sectional dimensions of a football field. Now, of course, this is no disadvantage to WMAN. They're not trying to contain their energy. They're trying to broadcast it over a large area of the state of Ohio. We, however, are trying to contain our energy and get it from the magnetron into the oven. At 2450 megacycles, we can easily enclose and control the fields. Pipe for transmitting microwave energy is called waveguide. This waveguide is usually slightly larger than the minimum sizes for reasons of efficiency. At 2450 megacycles, for instance, we use a waveguide that is 2 inches by 4 inches. The oven size, too, is related to the wavelength. The built-in oven is 18 by 14 by 15 inches. However, any size over 1 foot cubed can be used to good advantage for microwave cooking. Over that dimension, it is possible to distribute the energy so that good cooking results will be obtained. Now, of course, we need an oven large enough for a good-sized chicken or turkey or roast, or whatever the largest load is that we choose to place on the oven. Now, after an approximate size is picked in this method, an experimental program is necessary to determine just what type of an experimental program is necessary to get the energy from the magnetron into the oven. You don't just hook it up. You have to have the right coupling between the waveguide and the magnetron, and also between the waveguide and the oven cavity. How does energy in the form of electromagnetic fields create heat in foods? Well, the electromagnetic fields exert forces on the molecules. Molecules are pulled back and forth by the changing fields. Heating occurs because these molecules, as they are forced around by the electromagnetic field, rub against one another, creating heat by friction. As a simple analogy, think of what happens when you warm your hands by rubbing them together. The force with which you rub them together corresponds to the electromagnetic field strength, and the speed corresponds to frequency. There is a practical limit to getting an increased heating effect by raising frequency. This is so because the penetration of the energy into the food decreases as the frequency is increased. At 2450 megacycles, there is heating to a depth of 2 1/2 inches, which is to say that if you had some food that was 5 inches thick, the energy would penetrate 2 1/2 inches from one side and 2 1/2 inches from the other, and energy would be penetrating through the entire piece of food. Now let's look at some slides. Our first slide shows the action of microwaves in cooking. The energy is reflected from metal surfaces. It is transmitted by air, most glass, paper, plastics, and china. It is absorbed by food. And heat is only generated when the microwaves are absorbed. The next slide shows a simplified wiring diagram for the built-in electronic range. Let's take a look at these parts, and it will give us an understanding of what is necessary to make an electronic range work. This is the off-on switch. When this is turned to the on position, we go through 2 fuses and the magnetron cooling motor is energized, as well as the magnetron filament transformer. In this particular circuit, we have a 75-second time delay tube, which keeps the power off of this portion of the circuit until 75 seconds has elapsed and the magnetron filament is warmed up, and also the mercury vapor rectifier tubes have warmed up. We go through this fuse, and we see that as soon as we turn the off-on switch on, why the cooling fan is energized, and also the rectifier tube transformer. After the 75-second time delay tube, the oven light comes on, and we know that the oven is ready for operation. We have 2 door interlocks which must be closed before the oven can be operated, and also the oven timer must be set. When these conditions are met, the power relay closes the contacts in the high voltage transformer circuit, and the cook indicator light comes on, showing that microwave energy is being put out from the magnetron to the oven. The current regulator in this circuit operates to control and compensate for various voltage conditions, and also there's a high-low switch which controls the current through the current regulator, thereby giving a variation of from 900 watts in the high position to about 650 watts of usable power into the oven on the low position. When the power is put to the primary of the high voltage transformer, the secondary will put out about 5,000 volts to a full wave bridge rectifier circuit. The full wave pulsating DC then is fed to the magnetron, which converts it to 2450 megacycles and puts out about 900 watts. There's an antenna on top of the tube which feeds the energy into the waveguide, which in turn transmits it to the oven itself. The next slide shows the choice of cooking methods for various foods. The electronic range is not just for novelty items or quick demonstrations. It will handle most normal cooking. Now, individual taste will dictate how some items will be done. For instance, broiled tomatoes must be done under a broiler. Steak burned on the outside and raw on the inside should also be done on a broiler. It will not be done that way in a microwave oven because the microwave energy will penetrate into the center of the steak. Here we see comparative use of cooking facilities in homes equipped with electronic ranges. The recommendation is that one regular oven and two surface units act as companions to the electronic range. Compare the average times used per day of the various items in the household. Electronic range, 14 times a day. Top burners, almost 4 times a day. The oven and broiler, about once a day. The electronic range really handles a lot of traffic each day. Here we see representative cooking times. Electronic cooking is spectacular because of its speed. Here we see the greatest advantage is in the case of the baked apple. Normally it takes 45 to 50 minutes to do, but in the electronic range it takes 1.5 to 2 minutes. The least advantageous is asparagus, in which case it normally takes 18 to 20 minutes, but in the electronic range it takes 8 to 10 minutes. The next slide shows a comparison of meal preparation times per day in homes equipped with electronic ranges and in homes not having electronic ranges. The meal preparation time is what's important to the homemaker. Let's see what sort of variations we come up with here. In this case, we see that one person spends as much as 80 minutes per day with an electronic range, and here's one that spends 85 minutes a day without an electronic range. That doesn't look like much of a favorable advantage for the electronic range. But on the other hand, here we have one case where a homemaker was spending 35 minutes per day with an electronic range, and here's one that was spending 210 minutes per day without an electronic range. Now, of course, a statistical approach is necessary for accurate comparisons. So these are the figures that are important. The average time spent per day with an electronic range was 52 minutes, whereas the average time spent per day without an electronic range was 127 minutes, or approximately 2.5 times longer. This last slide shows the increased nutritive values that may be expected by cooking food in the electronic range. We see we can expect more vitamin C, more thiamine, more riboflavin, and more of the essential amino acids which are the building blocks of protein. There are other advantages to microwave cooking, such as the fact that foods can be cooked on the serving plates. There are no temperatures to remember, and they're economical to operate. For instance, leftovers are more appetizing when cooked in electronic range. Now that's something that you may not believe, and you probably won't believe unless you experience it, but it really is true. The electronic range uses power for a shorter period of time. While it's on, it uses approximately as much power as a conventional oven, but it's on, of course, for a much shorter period of time. The electronic range is also easy to clean. Foods don't burn on the oven walls because the walls are cool. Also, spattering foods can be covered. These are the advantages. Now, all, of course, is not rosy with the electronic range, or everyone would have them today. First of all is the price. The present price is $1,200 for an electronic range. This price is going to go down very shortly when new units come out with a new magnetron and new power supply. They will then be sold for approximately $895 or a $300 cost reduction. That's fine, but it still is rather high for the average person to afford, especially considering that he still needs a conventional range and surface units. The microwave energy will not brown. The internal heating produced by it does not result in the searing temperatures at the food surface necessary for browning. Therefore, browning units have been built into the unit that is sold right now, and is also present in the last range that we built. Microwave cooking is no advantage where tenderizing is necessary, such as in the case of tough meats or lima beans. In cases such as this, it is not enough to bring the food up to a given temperature. It must be maintained at a temperature for a sufficient length of time to break down the connective tissues in the food, thereby tenderizing it. For applications such as this, surface units are recommended. There's also uneven heating to some extent. For instance, casseroles should be stirred while they're cooking so that they will heat evenly. Experience is also necessary to do an effective job of cooking with one of these ranges, because cooking habits must be changed, and there's always a great resistance to change. Cooking habits have been built up over generations and generations, and they aren't about to be changed overnight. That's one of the difficulties that we're going to have even when the price of the range does come down so that a lot of people could afford to buy them. Also, more work needs to be done on yeast products. Well, so much for ovens. Microwave energy is readily absorbed by water, so clothes drying would also seem to be a good application. Let's take a look at the energy requirements in drying a load of clothes. 1 kilowatt hour will evaporate about 3 pounds of water. A 9-pound load of clothes will hold about 9 pounds of water, so we need about 3 kilowatt hours. In our 2450 megacycle equipment, we have 1 kilowatt, which means that it would take 3 hours to put out enough energy to evaporate the water in a 9-pound load of clothes. At 915 megacycles, we have equipment that will generate 2.5 kilowatts of power, which means that it would take approximately 75 minutes to put out enough energy to evaporate the moisture in a 9-pound load of clothes. The laundry equipment sales department was very much interested in having us build up a demonstration unit to prove that microwave energy could dry clothes. They wanted to show this at the Merchandise Mart in Chicago. This was several years ago. Now, of course, for something like that, they need a short time cycle for their demonstration. People aren't going to be standing around for 1 and 3 hours to see a load of clothes come out of a microwave dryer. An ordinary dryer will do it as fast as we could do it, even assuming 100% efficiency on our part. So that would be nothing spectacular. What they were after was a demonstration that would take approximately 1 minute. Well, in 1 minute, 1 kilowatt will evaporate 0.05 pounds of water. 0.05 pounds of water is the water that would be retained in a short-sleeved synthetic material sport shirt after it had been spun dry in a laundromat. And now, of course, after it's been spun dry in a laundromat, it doesn't need any drying. It's ready to be ironed right then. To evaporate 9 pounds of water in 1 minute would take 180 kilowatts. The cost of RF power, radio frequency power, is about $1 per watt. That means for $180,000 approximately, we could have enough power to evaporate 9 pounds of water in 1 minute. Needless to say, it didn't take long to decide which direction we were going to go. They started looking around for a way to make the evaporation of 0.05 pounds of water look spectacular. Well, so we started to work on it, and we found that the microwave energy was having trouble finding such a small quantity of water. When we get down to the last 1 or 200ths of a pound of water, the energy was having trouble finding the moisture, and it was being absorbed by other parts of the dryer. Now, we said that energy is not absorbed by plastics or metals. To a certain extent that is true, and to a certain extent it is not true. To the extent that metals are perfect conductors, it is true, but we know that metals are not perfect conductors, so they will absorb some energy. Plastics are not perfect dielectrics. They will absorb some energy. And some plastics will absorb a great deal of energy. Take, for instance, the nylon shirt that Harry Barker loaned us. Loaned us, I say. He never got it back. We put that in the dryer, and the dryer started out doing a pretty fair job of drying the shirt. But when it got down to the last few hundredths of a pound of moisture in the shirt, the energy, as I said, was having trouble finding the moisture. It didn't have any trouble finding the nylon. Nylon is one of those things which will absorb energy. So we ended up with some melted nylon, a shirt sleeve, some seaming in the shirt, which was not entirely dry, and all in all, we didn't have something that Harry was going to wear anymore. So this turned out to be a rather poor application for microwave energy, to say the least. Now, incinerators also offer a technical possibility, although, of course, there would be no thought of any economic possibility. Incineration is really only one step beyond cooking. Some cooks do incinerate on occasions. Speed would be unimportant, because it would just be a matter of getting a fire started. But as in the case of the dryer, after the moisture is gone, or at the time when there is very little moisture left, the microwave energy has a hard time finding the food. It's absorbed by other things, reflected back to the magnetron, and just doesn't provide the heat necessary to bring the food up to an ignition temperature. We started out our experiments with small hopes, but nevertheless there were some hopes there. Our first test, I believe, was with an onion. We turned on the power and it dried the onion out and started the thing to burn while we were standing there ready to put out any fire, of course, and doused the thing. We never did find out if the onion ever would have consumed itself. We ran quite a number of tests after that and couldn't get any fire to start. It just seemed to be a freak occurrence that we got any fire to start the first time. So incineration doesn't seem to be a good use for microwave energy either, but it was a thought and something we wanted to try. This is a brief story of the activities that we've had with microwave energy and concludes our description of our microwave energy program. I think you will agree that the microwave cooking is far more than a novelty. Cooking offers many advantages that are important to today's homemaker. It also offers a challenge to us to perfect this method of cooking and to put a microwave oven on the market at a price the average family can afford to pay.
This talk was given as a part of the engineering seminar program on June 12, 1959.